All right, so here it is. I have a solid disk, hollow sphere. I know there's some tape in here. I just tried to get the masses to be equal. Which one do you think is going to roll down this ramp first?
All right, so in this video, we're going to continue talking about, this linear to rotational equivalence. Okay, so we've talked about position, we've talked about velocity, we've talked about acceleration, we talked about force. Now let's talk about mass, right? So how does mass fit into this whole area? Okay, so in this video, we're going to talk about moment of inertia. All right, so any object, whether moving linearly or rotationally, wants to resist. All right, so it wants to resist changes to their motion, right? That's inertia, right? So remember, we called that Newton's first law. We gave it the name the law of inertia, right? Because it wanted to resist. Heavy objects resisted more, lighter objects resisted less. And the physical quantity associated with inertia is mass, right? So again, there is a rotational equivalent to this quantity, and we call that the moment of inertia, which is given the variable I, right? So this really determines how easy or hard it is to change an object's rotation, okay? Objects with high moments of inertia are difficult to start or stop rotating, much like high inertia or high mass objects are harder to stop or start. It's the same thing, okay? So the moment of inertia plays the same role of rotational motion that mass does for linear motion. And what happens is there's two factors that moment of inertia is directly proportional to. One is the mass of the object. So yes, mass plays into the object's rotational inertia. The second thing is that plays into an object's moment of inertia is the radius of the rotating object. Okay, in fact, it's the square of the radius. And we'll get into that here in 1 second when you see the general formula for the moment of inertia. Now, we're going to talk about specific ones that you need to know for the exam, but um, this is just the general equation. So I equals N mr squared. Okay, so the main part of the equation is this mr squared. But the n does play into this. The n in the equation is really a coefficient that shows how the mass is distributed. Okay. The greater the value for n, right, the further the mass is concentrated, which means the harder it is to change the rotational velocity. Now, the mass is more concentrated where the torque is applied. Okay. And so there are 5 basic rotational inertias that you do need to know for the exam. And so there are the point mass, the hoop or a cylindrical shell, a disc or a solid cylinder. I don't know why that says how does or how do. Okay, a solid sphere, and then a hollow sphere. Okay, so there are differences with the way these are addressed. If you think about like a solid sphere versus a hollow sphere, where is most of the mass concentrated in those, right? Same thing with the hoop and a disc, right? They're basically the same shape, just one's hollow and one is not hollow, right? So for a point mass, the moment of inertia is mr squared. So when we talk about that n value, so for uh, a point mass, the n value would be 1, right? That coefficient would be 1. All right. And then grab my purple, been consistent with purple. And so with a hoop or a cylindrical shell, again, we're going to do mr squared. And again, n is equal to 1. Now for a disk or a solid, or sorry, a disk or a cylinder, a solid cylinder, it's going to be 1/2 mr squared, where our n is equal to 1/2, right? And then for a solid sphere, the I would be 2/5 mr squared. And again, if we keep tracking our n's, n will be 2/5. And then our hollow sphere would be 2/3 mr squared. And our n would be 2/3. Okay. And so the way you think about this is, if we were to organize these in terms of which ones are harder, or from easiest to rotate to hardest to rotate, you're really going to start looking at that n value, right? And so this would be the easiest, the solid sphere, because look at your n value, it's the smallest. And then these two would be tied for the hardest, right? Because the n value is greatest. Okay. And then you would have, so you would, if you would go for easiest, 1, 2, 3, and then these would be tied at 4. Okay, in terms of which one's the easiest to hardest, right? And so they love these questions about which one hits the bottom first. So a disc and a hoop are the same mass and radius are released at the same time at the top of an inclined plane. Does the disc reach the bottom of the plane before, after, at the same time as the hoop? And then justify your answer. Well, what we do is really we think about the n values, right? That coefficient, and the smallest one reaches the bottom first because it's easiest to get it to rotate. So the disc, right, reaches first, right? So it reaches before the hoop. Why? Because it has the smallest moment of inertia. Sorry, my sentence structure is not making sense right now. Would help if I have the pen. Right? And so the disc is going to reach the bottom first because it has the smallest moment of inertia. Now, a lot of people will say the hoop because it has, the more mass is concentrated at the outside. But again, the more the mass is concentrated towards that center, that what really amounts to the axis of rotation, the easier it is to get that object to move. Okay. Now, again, this is going to start our conversation talking about rotational dynamics.
So there you have it. As predicted, it was the solid cylinder.